Hey folks, today we're going to learn how to draw LOL diagrams. And these are diagrams that help us analyze where energy is being stored and how energy is being transferred in physical situations. We call them LOL diagrams because, well, they look like LOL. And so it's just kind of fun, and we also think that we're being really cute. One of the most important parts of creating an LOL diagram is really understanding which of the energy storage modes are present and in use during whatever situation we are analyzing. And we're mostly going to be dealing with these top four in our list of common energy storage areas. Remember, kinetic energy, that is the energy stored in the motion of an object. It's important that you learn the symbols and you learn to recognize kinetic energy. If something is moving, then we have kinetic energy. The symbol is a capital E with a small k subscript, but I also use, you'll see me use KE. That's just a traditional common way of symbolizing kinetic energy. I keep trying to switch myself to EK to kind of emphasize that it's just one type of energy and we have these different then storage areas for it. But old habits are hard to break. Gravitational energy, important. Remember, that is the energy stored in the position of an object in a gravitational field. We're going to use that all the time. Elastic energy is probably the one we'll use that anytime we have some object that is stretching or being compressed or squished that wants to kind of snap back to its normal shape. This is usually a spring or some sort of rubber band, like a scrunchie or something like that, that has that elastic property of being able to be deformed in some way, but then it wants to come back to the way that it was at the beginning, what we would call its equilibrium state. And finally, thermal energy, E-thermal, and we're going to deal with this mostly because we deal with friction. And any time that we have friction in a problem or that we have to consider friction, we're going to have to consider that thermal energy, that heat that is being generated when two objects are rubbing together or are colliding together, and where that heat energy, that thermal energy then is being transferred. So an LOL diagram shows us where energy is being stored in a system, and it also tells us whether energy is being transferred into the system or out of the system, or even if the energy is being transferred from storage mode to storage mode within the system. And we do that by taking kind of snapshots, moments in time, where we analyze where the energy is being stored, and then we look at what events are occurring and whether that involves some sort of energy transfer. Now, each L in the LOL diagram shows us a specific moment in time. It's like if you could take a snapshot and then you could take a look at where is the energy being stored at that moment in time. If we take a look at our first L right here, then what we see is that we have a little axis, and we're going to eventually create little bar graphs here showing which of the storage areas we have energy being stored in and maybe which we don't. Notice here that we have a labeling system, and we're going to always include on all the L's in a specific LOL diagram any energy storage area that is present in that entire system, in that entire situation. In this case, notice we have kinetic energy, we have gravitational energy, and this is elastic energy. When we get to the O's, the O represents the system, and it's going to tell us which objects are in the system and which objects are outside of the system, in the surroundings or the environment. We're going to do that by actually drawing in or writing in the objects that are in the system in the O. And any objects, including air, that are outside the system, we're going to write outside the system. And then what will happen is we're going to show with arrows into or out of the system, we're going to show energy entering or leaving if it does. Now, the actual size of the O is representing how much energy is in the system. And we'll talk a little bit more about how do we work with that in just a minute. So a basic LOL diagram is going to include 2 L's and 1 O, like you see on the top diagram here. What that gives us is 2 moments in time, and each moment in time is represented by an L. So this is moment in time 1, and this is moment in time 2. And it gives us 1 system O in the middle. And you're going to want to draw that O in the middle big enough that you can write in it, because you're going to have to make a list of all the objects in the system in it. And you want to leave enough space that you can write any objects outside of the system in it. It just kind of, you do your best, and you'll learn as you do it how big you need to draw things. Now, each L is a labeled axis that gives us any of the storage modes that are present in the entire situation, okay? So in order to be labeled, an energy storage mode only has to be present at one moment in time. But we put it on every single L for every moment in time so that all of our L's are labeled the same way. This first diagram, we have our kinetic energy, gravitational energy, and we have our elastic energy. If I have to consider friction and there's thermal energy, I'm just going to add thermal in there. You just put into that labeling system at the top of each L, you put that in, whichever ones that you need, and then you carry that through the rest of the diagram, even if you no longer need it. Now, notice that there are no numbers on our axes, all right? We're going to be creating bar graph type things on the L's here. And so we have our different areas across the horizontal axis, our different storage modes, and you're not seeing numbers here. Most of the time with our LOL diagrams, we're going to be doing semi-quantitative diagrams. You're going to just choose a relative amount of energy, and then that's what you're going to work with. And that will make more sense here in a little bit. This is a traditional LOL diagram. If you look at the diagram on the bottom here, though, notice that it's a little more complicated. This one is an LOL diagram. And notice here we have 3 moments in time. We have 3 L's. We have 1, 2, 3. We have our initial system, O, but then I've added another system O. Now, this is optional. If nothing changes in the system, if the total amount of energy remains the same, there is no energy coming into the system, there's no energy leaving the system, after you do the first system O, you can skip it. And then you would have an LOLL diagram. But if there is energy entering the system and you're changing the amount of energy in the system, or if energy is leaving with the same result, then you are going to need to draw another O. And that O should be bigger if there's more energy in the system, because some is being added, or it should be smaller because some energy has left the system. And we'll practice all of that too. And so you can have 5 L's if you want. You can have 3 O's. You can have whatever combination of L's for moments in time that you're looking at, and O's that represent the system and any changes in the overall energy of the system as you go. Okay, so let's start to look at an example. We are going to track how much energy is in the system in every L, and any energy that is entering or leaving the system in every O. So here is an example. This is an LOLOL diagram. We have 3 moments in time. We have 1, 2, and 3. We have a system here. There's nothing written in there. So we can imagine several situations in which this LOL diagram might apply. And the first one, I'm going to say for situation number 1 that I have a person and they are holding a ball. That's a person holding a ball, folks. And because they're holding a ball, here is the ground. There is some height above my gravitational 0 line. I'm going to say my gravitational 0 line is the ground itself. So my gravitational energy is 0 there. And the person is just holding the ball still. And what this means is there any kinetic energy? No, because the ball's not moving. I like to draw little X's on my horizontal axis if there is no energy being stored in that storage area. It just helps me realize that, yes, I've actually looked at this. And there is gravitational energy. So I'm just going to randomly kind of say that there is a block of gravitational energy. You know, this person could be holding it higher, in which case there might be 2 or 3 blocks, but it's not on the ground, so there's not 0 blocks. So I just gave it 1 block. And then I'm going to take a look at my elastic energy. There's nothing stretching here or being smushed together, so there's no elastic energy present. Okay. Now, if I take a look at the second L, in that moment, there is more gravitational energy. And so that would happen if this person on the ground raised that ball up high and kind of lifted it up, applied a force to raise the ball up higher. Now, if the person is just holding the ball up higher now, there's no kinetic energy because the ball isn't moving. There is more gravitational energy because now, look, I have a bigger height. And there's still no elastic energy because there's nothing stretching or compressing. And finally, in my third LOL, note that I have some kinetic energy. So now the ball's moving, and now I am back to having 1 block of gravitational. So, okay, I think what's happened here is the person standing on the ground has dropped the ball. And now the ball is whoosh, 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 flying down toward the ground. I'm back to having just that initial amount of gravitational energy, but because it's moving, I have some kinetic energy. And again, no elastic energy because nothing is stretching. Now, as I examine what is going on between these 3 moments in time, I realize a few things. First of all, in moment number 1, I have 1 block of EG. In number 2, I have 2 blocks of gravitational energy. Well, wait a second. If I have more energy in moment 2 than I had in moment 1, then where did that energy come from? Well, it came from the person lifting up, applying a force to the ball. And so the person did working, and we'll define work and all that stuff later, but the person put the energy into the system by raising the ball up higher. And so we can draw an arrow into the system showing there's going to be energy into the system. And then how much? Well, I started with 1 block and now I have 2. So there's 1 block of energy. There's different ways of drawing that and showing it. And you can find one that works for you. Okay, now from the second to the third moment, the amount of energy stays the same, but it's more than the first moment in the system. So when I draw my next O, it's going to be larger because there is more energy now in the system. And I'm going to make sure that I have the same amount as I had in moment 2 here. So here I have EK plus I have some EG. So hopefully this helps you kind of see how we start to analyze the situation a little bit. And what we're going to learn to write equations using these kind of numbers and symbols, but we'll get there in just a minute. Now, this page gives you a sort of process to go through to help you create an LOL diagram. And especially when you are beginning, just follow this process through every time. And once you kind of get a feel for how to create these LOL diagrams, you're going to develop your own process. The important thing is to be systematic, because we always start with kind of simple, straightforward problems, and then we get things that are more complicated. And so there's a tendency to want to just kind of, gut it through on, follow your instincts. On the simple problems, but then when you get to the complicated ones, you get stuck because you're like, I don't know what to do, because you never had a thoughtful, systematic approach to how to solve the problem. So here is what we're going to do. We are going to define the system, and there are some things to think about over here. I'm not going to go through every single one of them because you can read. You're going to identify which energy storage modes are involved in the moments that you care about, that you want to look at. You are going to identify whether any energy is going to be coming into the system or leaving the system. Does the total amount of energy in the system change from moment to moment? You're going to draw your initial L for the before state and fill it in. You're going to put the labels on it, and you're going to draw whatever your starting amount of energy is going to be in blocks. And then you're going to draw the initial O to represent the system. You are going to write all the objects in the system including air, if that's included. And you will draw any energy transfer that is immediately, that that's going to go in there. And we'll talk about how to draw that. And finally, you're going to draw the next moment in time, the L. You're going to label it the same way that you labeled the first one. You're going to fill it out. Where is the energy being stored? And you're going to keep going for as many moments in time as you need. You may have 1 L, 2 Ls, 5 Ls. And you may then, between each moment in time, is the system changing? Is there energy coming in or leaving? If there is, you've got to draw another O. If there's not, you can stack the L's next to each other. You don't have to redraw the system every single time. Let's do some. Let's try some on our own. All right, now let's try some of these. For the first one, that blue problem there, what I would like you to do is pause the video here in just a moment and try and draw an LOL diagram for it. Use that system, that slide that I just went through with you. I've dropped that into your OneNote so that you have that actual slide. You can put it on your phone, you can print it out, or you can just have it up on your OneNote and you can be using it. And then when you think you've got it, or you've gotten as far as you can get, then start the video back up and let's go through how I would draw the LOL diagram for problem number 1. Okay, now here's how I would draw this. Let's read the problem. First of all, it tells us up front that we are going to ignore air resistance. That's great. That air resistance is just kind of like friction with the air. And that means that we don't have to have heat. We don't have to worry about energy leaving the system because the heat is being transferred into the air, into the surroundings. It also tells us a soccer ball is sitting still on a field. Then a soccer player kicks it up. We're going to assume straight up, okay? I am at least. And we want to draw for the moment the ball is at its highest point. Then the ball falls back down to the field, and we draw for the moment just before it hits the ground. Now, I'm going to draw 3 L's here. My first L is going to be for this moment here where the soccer ball is on the ground. My second moment is going to be here for when the ball is at its highest point. And my third moment is going to be here where the ball is just about to hit the ground and it's traveling at its fastest speed as it falls. So I'm going to draw an L. I'm going to draw an O. I'm going to try and keep my O kind of big because I need to write in it. And I'm going to draw an L. I know I have another L coming, but I'm going to start with these 2. I'm always just going to go one moment to the next when I draw. And I need to take a moment here and I need to think about what objects are in my system. So in my system, I'm going to have the ball. I'm going to have the earth or the ground. And I could put, the foot in the system, the soccer player could be in the system or outside the system. That's kind of up to you, how you want that to be. You could draw a perfectly correct LOL diagram having the soccer player in the system, or you could have one drawing him outside the system. I kind of want to focus on what's happening to the ball, and so I'm going to put the soccer player outside of the system. Like such. Now, I'm also going to take a quick look next at where is energy being stored. I know that I have a ball that is changing its height. So that's my signal that I'm going to be dealing with some gravitational energy. So I'm going to write gravitational energy in here. And then as I think about the situation, the ball is going to be moving. It's going to be moving up and down. So if the ball is moving, I've got to have some kinetic energy here. So I'm going to put some kinetic energy in here. And anything I do to one, I've got to do to the other. I don't need to think about heat, thermal energy, and air resistance. So I don't need thermal. Right now, I don't think I need any other energy storage modes, okay? So let's now start to think about what's actually happening here. In number 1, here's number 1, my first L, a soccer ball sits on the field. Okay. And my gravitational 0 line will be the field itself. There's nowhere else that the ball can fall or sink to. So I'm going to call that my gravitational 0 line and pretend that there's no gravitational energy there, even though clearly the only place, where there's not going to be gravitational energy from the Earth is at the very center of mass of the Earth, but that's a whole nother story. So I don't have any gravitational energy. So, okay, I'm just going to put a little X on my axis there. And if the ball is sitting still on the field, I don't have any kinetic energy. Now, you might at this point feel a little uncomfortable because, wait a second, I thought we were looking at energy storage and I'm saying there's no energy. And is there ever really a situation where there's no energy present? Well, no. We are simplifying things way down and we're only considering a few of the basic energy storage modes here. It's okay if you have a situation in which there looks like there's no energy present in the storage modes that you're caring about, that you're looking at. Where does the energy actually come from here? What starts the ball moving? It comes from the soccer player's kick. The soccer player is putting energy into the system. And I'm just going to draw an arrow that goes into that system O. And I can decide how much energy is going in. I'm going to say that he's going to put 2 blocks of energy. I like to draw it like this. Some people like to draw an arrow in, I'll show you on the next one. Some people like to draw the blocks right into the arrow itself. It's totally up to you. Okay, so I have my soccer player transferring energy into the system by kicking. That's a force. Kicking is applying a force, a push or a pull on the object. And so, of the three energy transfer mechanisms that we have, this is going to be working. And so I'm going to label it W. I have 2 blocks of energy all going into the system from the soccer player. And then in moment 2, the ball is at its highest point. The ball is going to go up, and then it's going to come back down. At that top moment right there, the ball is actually going to stop for a moment as it changes directions. And that's the highest point the ball is going to go. If the ball stops at that moment at the highest point, well then guess what? No kinetic energy. So I'm going to draw an X there. But I am going to have plenty of gravitational energy because I'm at my highest point off of the ground, off of my gravitational zero. So I'm going to draw 2 blocks of energy there. Because if I'm putting 2 blocks of energy into the system, I've got to have 2 blocks in the system. I have to be consistent. Okay, now I do have a third moment, and I need to decide, do I need to draw another O? Well, I do, because my system has changed. I went from having this relatively small system. I'm now going to have like a great big system. I'm trying to draw that bigger. Okay? You don't have to label it again. As long as you label the system in your first O, that's totally fine. But you want to show that it's bigger. If you have paper, you can make yours much bigger. It's totally up to you. It's a little tricky when you got to write in them. And then I am going to have an L for my third moment in time. I'm going to label this. There's my gravitational, and there's my kinetic energy. And I'm going to analyze where is the energy being stored as the ball falls back to the field at the moment just before it hits the ground. Okay, so if I am right at that moment before I hit the ground, then I'm not going to have any gravitational energy because I'm essentially at ground level. All right, I'm right on the 0 line just before it hits. So I'm going to have no gravitational energy, but that ball's really going to be moving fast. And the faster the ball moves, the more kinetic energy I have. All my energy now is going to be stored in the kinetic energy of the ball. Now, I don't need to draw any arrows in my O here because I'm just transferring that energy within the system, and it's the same amount of energy. And we only draw the arrows if energy is coming into the system from outside, from the surroundings, or if energy is leaving the system and going out into the surroundings. The last thing I want to do here, I'm going to change color one more time here, is I want to kind of draw a little equation here. I want to look at what I have. In my first moment, 1L, I have 0 energy showing. And then for the first for the first O here, I have plus work. Okay? And that has to equal all the energy in the second L. And all that energy is gravitational. I don't add or subtract anything here. And that gravitational energy has to equal the kinetic energy at the end. And so I'm able to kind of track, once we have equations for solving for work and solving for gravitational energy and solving for kinetic energy, we suddenly have a real chance to calculate some information about our situation. Now, you stop this recording right now, and if this is, you need to look at anything or this isn't making sense, take a good look at what I've done, compare it to what you did, and see if you understand why I made the choices that I made. I'll give you just a minute here. Okay, now I would like you to try the same thing with the green problem. Go ahead and pause the recording, you do an LOL diagram, and then we'll come back and you can see how I do it and compare your choices to mine. Okay, so here's how I would approach this problem. First of all, when I look at this problem, I note that I have a ball sitting still on a table, then I have a person pushing the ball, and then the ball is rolling across the table. That's my second sort of snapshot, one moment as it rolls, and then the ball stops. And the big caveat here at the bottom, include friction. So I'm seeing three snapshots, three L's. The first when the ball is sitting still, the second when it's moving across the table, and the third when it's come to a stop. And I have to include friction, so I need to make a choice about that. If I have heat being generated by the ball rolling across the floor, then I'm transferring some of that energy into thermal energy. And that thermal energy is going to escape into the air. And so one of my first choices is going to be, what is my system? What am I going to include in my system? I'm just going to draw my LOLs here. And in my system, I'm going to definitely include the ball. I'm going to include the table that it's rolling on. And if I want to kind of simplify things, sometimes it's simplifying, other times it's not. But if I want to simplify things, I'm going to include the air, because that's where the heat is going to dissipate into. It's going to kind of escape into the air. A little of it will escape into the table. And that way I'm keeping that thermal energy, that heat energy, I'm keeping it in the system so I can track it. And I'm going to make the same choice that I did in the last problem. I'm going to put the hand outside of the system. And then when I go and I look at where I'm storing energy in those snapshot moments, well, I definitely have a ball that's moving. So I'm going to have kinetic energy. I'm going to assume my tabletop is gravitational zero because the ball is not going to fall through the table. And the ball is going to just stay on the surface of the table. So I'm not going to have any gravitational energy because the ball will not have any height above the table. So, okay, that's cool. And then I am going to have that thermal energy from friction, so I need to write that in. That TH is not great, but oh well. Okay, I think I'm ready to start to actually think about this. And when I look at this, my first thought is, okay, a ball sits still on the table. This is snapshot one. There's no kinetic energy being stored because there's no motion of the ball. Nothing's moving. And because there's nothing moving, there's no friction there that's causing heat that's going to transfer energy into heating and thermal energy. So I don't have any there. Okay, same situation I had up top, no energy in number one. Snapshot two is after a person gives the ball a push. So I know that a person is going to apply a force to the ball and is going to put energy into our system. And so I'm going to draw a different kind of arrow this time. Some people prefer to draw these kinds of arrows where the arrow is kind of a blocky thing. And then they show how many blocks of energy they're putting in by like marking the arrow that way. So I would be putting in 2 blocks of energy, 1, 2, into the system. And because I'm applying a force, that is through working. And now I have 2 blocks of energy to deal with. I now will have some kinetic energy, excuse me, because the ball is rolling across the table. So let's say I have a block of kinetic energy. And I'm also going to have some thermal energy because I have friction, which is generating heat, which is escaping into the air, which is still in my system. So I'm tracking that thermal energy, and I'm just going to say that I have a block of thermal energy. These should be equal, even though I drew that a little big. I would now have to consider, what am I going to do next? I do need to draw another O because, and I'm going to make it kind of big. It's kind of skinny, but I'm trying to make it bigger to show that there is more energy now present in the system because of the work that was done by the hand on the ball. And I'm going to have my final L. Here's my EK and my thermal. And what I will see, if I think about it, is that at the third snapshot moment in time, the ball has come to a stop. So there's no kinetic energy. All the energy in this case would now be thermal. And so I would have 2 blocks of thermal energy. And if I'm writing that equation like I did last time, I'm going to have 0 plus work equals, oops, yikes, sorry guys, EK plus E thermal, which is going to equal, because I'm not adding or subtracting anything, any energy into the or out of the system, equals all E thermal. How did you do? Go ahead and stop the video here if you need to and compare and see how your LOL diagram came out compared to mine, and whether you made different decisions than I did. And it's okay to make different decisions than I did, as long as they're physically appropriate and they're internally consistent. This is how you do LOL diagrams, and now we are going to practice a whole bunch more.